We continue with the language of standard model and see what it has to say about phase transition particles from one state to another. We are looking at the phase diagram of the particles from state now to the early universe. It is just like the phase diagram of any other element of nature, with same complexities involved, the same phases of transition from solid to liquid to superconductivity, with only difference of the requirement of temperature and the requirement of recording and knowing different states of matter. To understand the early cosmos, we need extremely high energy to move to that state of matter only few seconds before Big Bang. In the range of low to moderate temperatures and low to moderate baryon density, there is density of quarks and gluons, we can find our everyday world of solid particles, the solidity around. It is a state of confinement where gluons, the strong force carrier, and the quarks get confined. We can't find them free. What we can see are the hadrons, the protons or neutrons, where the quarks are bound. The quarks are bound by the gluons, the strong force, and it is very difficult to separate them and to see them in isolated state. Or as the critical point or critical temperature of 100 mega electron volts is reached, we see that the phase transition starts. Even if the density of baryon is moderate, we can see the phase transition. We see a sea of quarks and gluons moving freely. We can detect them by different methods. We can measure them by different methods. Quarks move freely and change from one type of quark to another type of quark, and there are so many particles out there, and there are free gluons moving everywhere. And at the highest temperature of 200 mega electron volts, we get what is called a plasma state. A quark gluon plasma is formed. At very high baryon density, a next striking phenomenon which is found is that Cooper pairs are formed. The quarks and gluons form Cooper pair. There is chiral symmetry breaking. That is, the pairs or the particular manner in which the pairs used to combine in confined state, there is no bar for that. In the deconfined state, the pairs can combine in any form, in any way. That is, chiral symmetry is broken. And so with the gluons. Any two colors can form a pair. That is what we call the color symmetry. Picture that emerges out. With the basic particles of gluons and quarks are the basic massless particles of universe, and other particles like photons, carriers of electromagnetic force, the weak force of W and Z bosons, which is a long range force, the graviton, which is a very strong force at long range, but a very weak force at short range, and gluons, which is a very strong force. All these forces are needed in the makeup of the atom. The strong force keeps the hadrons and quarks confined in the nucleus and binds the protons together. The weak force helps us in binding the neutrinos in the setup, and electromagnetic force, which is found outside nucleus as well as inside the nucleus. All these forces make up the cosmos we see. The gluons and the quarks have what we call color charge. There are three color charges: red, blue and green. The color represents the nature or the strength of the charges involved in three types of charges, and when they combine, they give what is called the conservation of charge in our observable universe. That is, they must combine in a particular way, in a particular combination, to conserve the charge of hadrons in the state now of universe. But that conservation of charge is not preserved when we move to the deconfined state of universe or early universe. The gluons can have two flavors or charges, color charges out of these, while the three quarks have the three flavors or three charges in all in a head. So what we find is that a simple picture emerges out. All of these forces differ only in the range of their interaction or the strength of their interaction, and they are expression of some same basic thing at the backdrop, and the probable candidate is Higgs boson, which gives mass to all of these particles. There is a candidate which can explain all these interactions, and we know the candidate from our simple physics, that is coupling constant. The coupling constant is a candidate which can explain the range and strength of all the forces. I'll be dealing with the coupling constant in a full separate video. The electromagnetic force we know very well. The force of interest here is the unlimited force between quarks and gluons, which is the strong force. You can see in a hadron the quarks exchanging the gluons and binding together. The gluon is so much strong that as the quark is pinched off, the another quark gets formed, and as the quarks keep pinching off, the gluon strength gives birth to another quark at the point of. In the deconfined state, they keep forming different types of particles and giving birth to different states of particles, different types of